Yeah, thank you, Professor, for a brief introduction. So I just take this opportunity to introduce the fundamentals of the matrix decomposition and how we'll be using this in machine learning. Okay. Yeah. Can you hear? Okay. So can you see the slides?
Yes, sir.
Yeah. Great. Yeah. Thank you. So the topic structure is like this. So initially, I'll start with the basics of like matrix. We have to find the determinant and the traces. Then we'll shift into finding the eigenvalue and eigenvector. Like we'll understand what is eigenvalue and eigenvector. Then we'll try to utilize these eigenvalues and eigenvectors in LU decomposition, and also then we'll use SVD. Finally, I'll end up with demonstrating the implementation of these eigenvalues and also SVD. Okay, so I have some four examples to demonstrate. Okay, so to begin with, what is basically a matrix decomposition is and how it will be useful. So in a machine learning, of course, we know that we have a huge set of data, and these data are represented in a matrix, right? And to evaluate something or to make some decisions, we have to know that how exactly these matrices or these features are behaving. So that's the reason in a matrix decomposition are very useful tool for reducing a matrix to their constant parts. In order to, we are just trying to simplify the range of more complex operations and try to analyze the numerical stability of a system. Right. So basically, this was used to solve a system of linear equation, and it started in the year 1970. Right. Most of the frequently used decompositions like LU, QR, Cholesky, Jordan, spectral decomposition, and singular value decompositions are used. Right? Now, what exactly a data is represented generally? Let's take one simple example of a socio people, So where we try to represent the different peoples in rows and their features in columns. Okay, so this matrix has features of like height, weight, color, and sex, and set of peoples. This is how generally we try to represent any matrix. You have a set of rows and columns. Basically, rows will be represented with the people. In this example, as a people and their features. Right now, how do we start with this? When we talk about the final thing is when we learn a matrix decomposition. So this will be used in applying for some applications. So when we say, so let's take an example of image compression. Okay, so obviously when we try to compress these things, we have to represent, let's say if I am using SVD, right? So I need three different components for that, where I need to find out the sigma, the column matrix, and also the vectors of this, so vector transpose of this. Now, to determine those things, these are the basics that are necessary. One is the determinant and trace. So I just go through this because we are already familiar with how do you determine the determinant of a matrix as well as a trace, right? So just to brief, basically a determinant is a mathematical object in the analysis and solution of a system of linear equation. and it is a quantity obtained by the addition of products of the elements of a square matrix according to some given rule, right? So how do we find a determinant? It's a function that basically maps A onto a real number. So determinant of A is A11, A2, A12 till A1n. So representing a set of rows, and you have a columns, right? Now a matrix is a singular if and only if the matrix has a determinant 0. This is one of the properties that you have to understand. So obviously a non-singular matrix does not have a non-zero determinant. Now, for any square matrix, if I consider to determine when you use a determinant, right? It holds that A is invertible if and only if determinant of A is not equal to 0. So now, for n is equal to 1, determinant of A is equal to A11 itself. For n is equal to 2, determinant of A11, then A12 minus A21, A12. Similarly, for 3, we'll use something like, suppose if I want to define a determinant of A11, obviously that is A11, A12, A22, A33, right? So now let me take one simple example of that. So basically, to find a determinant, okay. So let's say you have A, okay, having 8, 15, and 7 minus 3. Let us say that. Okay. Now this is the matrix. Now how do we find this? Of course, you know that the general is this into this minus this, right? So it means 8 minus 3 minus 7, 15, right? So that will lead to minus 24 minus 105. So the determinant is minus 129, right? So this is how we generally find a determinant of a matrix, right? So next is, right, and a determinant exhibits the following properties. So when you say that the product is the product of corresponding determinants. So determinant of AB is equal to determinant of A or into determinant of B. Similarly, determinants are invariant to transposition. That is, determinant of A is equal to determinant of A transpose. So if A is irregular invertible, okay, so then determinant of A inverse is equal to 1 over determinant of A. So similar matrices possess the same determinant. So therefore, for a linear mapping phi, so given V for all transformation matrices, A phi of phi have the same determinant. So therefore, the determinant is invariant to the choice of a basis of a linear mapping. So in these cases, we will try to add multiple rows or columns to another where it does not change the determinant of A. Okay. So basically, this the multiplication of a column or a row with a lambda which belongs to R. This scales the determinant of A by a lambda. So in particular, if you say determinant of lambda into A is equal to lambda to the power of n into determinant of A. So by swapping two rows or column changes the sign of a determinant. Okay. Now second thing is, once we know about the determinant, the next thing is the traces. So the traces of a square matrix A that belongs to a set of real number n cross n, which is defined as traces, right? So 1 to the power of n ai. Okay, so it means, so when we try to find it is basically sum of the diagonal elements of A. So suppose a given matrix A, right? So you have a 3 element 5, 3, 5, 4, minus 1, 2, minus 3, 8, and 7. the traces are the sum of diagonal elements. In this case, the trace is 11. So basically, we will consider the main diagonal for a square matrix. So the properties include, okay. So trace of A plus B is equal to trace of A plus trace of B for all A to B that belongs to R n cross n. Similarly, the second property is trace of A is equal to some alpha into trace of A, where alpha belongs to a set of real number for all A belongs to R to the power of n cross n. Similarly, for trace of identity, n is equal to n, and trace of AB is equal to trace of BA for all A belongs to R to the power of nk and B belongs to R to the power of kn matrices. Okay. Now, since you knowing these things, we will be using the Laplace expansions, where basically that is used that reduces the problem of computing the determinant of n cross n matrix to computing the determinant of n minus 1 cross n minus 1 matrix. Basically, it is computed by continuously breaking matrices down into smaller matrices until the 2 cross 2 form is reached. So suppose I have n cross n matrices. Okay, now in a Laplace expansion, we try to break these matrices until it reaches 2 cross 2. So to apply this matrix Laplacian expansion, let us consider a matrix where A belongs to R n cross n. So then for all J, okay, is equal to 1 to n, expansion along to generalize this along column J, determinant of A is equal to from k is equal to 1 to n minus 1 to the k to the power minus 1 to the power of k plus j, a kj into determinant of a kj value. Similarly, for along with the rows, if you are applying for a row Laplace expansion, determinant of A is equal to from sum of like k is equal to 1 to n minus 1 k to the power of k plus j, okay, ajk determinant ajk, right? So here basically, if you notice, akj belongs to r to the power of n minus 1 into n minus 1. So basically, it is the submatrix of A that we obtain when deleting row k and column j. So to demonstrate this, let's try to run one simple execute. Let me take one simple example. So let us consider a matrix, right? So as A11, you have A12, A13, okay, and you have A21, A22, A23, and you have A31, A32, A33. Okay. So now for this, so the minors are the minor of element A12 can be determined as A21, A23, A31, A33, right? Similarly, the minor of element A21 is A12, A13, A32, A33. Okay, right? So this is how we try to find a Laplace expansions in this. We just try to find we try to reduce this until we get a 2 cross 2. Okay, now from okay. Now let's try to understand what is eigenvalue or an eigenvector. Okay. So basically, if you see the definition of an eigen, the word, basically it's a German word. It means own or typical. That is a German that is atypical of them, something like that. So in English, generally we use a word called characteristics. So you can say that eigenvector can be called a characteristics vector. It means what exactly the eigenvector is. See, now we have an eigenvalues, a set of eigenvalues that has to be determined. Okay, so in that case, eigenvector basically that does not change the direction in a transformation. So when you perform a linear transformation, so hope you already come across what is basically a transformation is, right? So given I have some point and that point has to be projected, let's say this, okay, in a matrix. Now when we transform from one space to another space, suppose whatever the value that I try to find, okay, so when I perform some scaling operation here, so what is this scaling mean? When I try to stretch a specific positions, right? So the coordinates shifts from one position to another position. Either if I stretch horizontally or vertically, the direction does not change. So that's the reason we call these type of vectors as a special vectors, which does not change the direction. Okay. Now it means, see, suppose I have n number of vectors, right? So like one vector is moving into some direction, another vector into some direction, right? Now what basically we are trying to do in this by understanding the eigens here. So when we use try to find an eigenvalue of this, it means the factor basically that is allowing us to stretch that or to move that, So when the factor basically gives you the length of that. So eigenvalue is a scale of the stretch. See, for example, here, let's say this is a vector. Now we try to stretch this, right? So it means if I try to stretch this horizontally or vertically, right, the new position that it changes, the length. See, for example, this is length 1, let's say this. Now, suppose if the length increases, suppose if the length is doubled, so that is 2 lambda. Now, suppose if it is -1, means the same vector, but it is pointing in opposite direction. Okay, right? So there are a lot of applications of eigen values and eigenvectors in physics and also networks, right? Now, how do we find this? Now, hope you are clear with this, right? Now, I have a when we see when do I use this eigenvalue? Suppose in an image processing, I will try to reduce the image or to compress the images, or I will try to stretch the images. Now, when we do such things, right? So we should be clear. We should try to identify what are the vectors that does not changes its directions. So in this case, if you observe, the green color is another vector. See, we have 3 vectors here: V1, V2, and V3. When we stretch this, so when we stretch this horizontally, the position of the green vector has changed, right? The direction has changed here. Whereas the vector 1 and the vector V2 has not changed. The red color does not change. So that's the reason out of these 3 vectors, the vector 1 and vector 2 are the eigenvectors. Similarly, when we stretch this in a vertical direction, so it means we are transforming from one space to another space, or let's say we are trying to stretch the values, right? If you observe here, again, this particular vector has changed its direction, whereas the same way the vectors that is represented in red color does not change. right? So that's the reason we call these as a special vectors. Even after applying some transformation, it does not change the direction. So in an image compression techniques, when we try to reduce the images, we try to find the eigenvalues. That's the basic usage of eigenvalue, and we try to find the eigenvector of this, right? Now, how do we find this? How do we find a eigenvalue or an eigenvector? Okay. Now, basically, to find the eigenvalue, we know that the equation must be true. Suppose A is a matrix, right? And we have two vectors, B. A vector is equal to lambda into the vector V. So how do we determine this, right? So we know that a scalar lambda that belongs to some field is called as an eigenvalue of A that belongs to L of that particular vector. So if that exists, non-zero vector, right, where V small v belongs to a capital V, such that AV is equal to lambda V. So it means now, how do we find this? We try to use the determinant A minus lambda I is equal to 0, right? We try to find the determinant of this, right? So in this, we'll try to identify a specific eigenvalues, right? So let's take one simple example and try to find out the eigen vector, right? To find eigenvector and eigenvalue for a 2 cross 2 matrix. Okay, so let's consider a matrix A. Okay, so minus 6, 3, 4, and 5. Okay, so first it means first we must calculate A minus lambda I. Okay, so for that okay, minus 6, 3, 4, 5 minus lambda 1, 0, 0, 1. Okay, which is minus 6 minus lambda 3, 4, 5 minus lambda. Right. So now the determinant should equal to 0. Okay, so if you take this, right, you have minus 6 minus lambda 3, 4, 5 minus lambda, determinant equal to 0, right? So to solve this, right, so which is basically minus 6 minus lambda, 5 minus lambda, 3 into 4 equal to 0, right? So which will get as a quadratic equation, lambda minus 42 equal to 0, right? So and of course, since we have a quadratic equation, solving this, we'll get lambda is equal to -7 or 6, right? Okay. Now it means we have two possible eigenvalues, right? Okay. So now generally we consider the positive values first, right? So now let us start with AV is equal to, we try to apply this for a now we have got, right? So we have got lambda is equal to -7 and 6, right? Now to find eigenvector, okay? So let's start with AV is equal to lambda V, right? So here we'll consider lambda is equal to 6. Okay. So if you see substitute this, we are trying to find the, please remember, we are trying to find the eigenvectors. We have just obtained the eigenvalues, right? To find that, right? So we are trying to find this vector, right? So x, let's take two variables, x, since it is a two-dimensional, x is equal to 6 into x and y. Okay, right? So lambda, where v is, that is what we are trying to find. Okay, so 6 into x and y. So that will lead us to 6x plus 3y is equal to 6x. Then 4x plus 5y is equal to 6y, right? Okay. Now bringing all to the left hand side. Okay, bringing all to left hand side. Okay, so -12x plus 3y equals 0. Okay, and 4x minus y equals 0. So we have y is equal to 4x, right? So we have y is equal to 4x. So the eigenvector is any non-zero that is a multiple of 1, 1 and 4, right? So you have this is a eigenvector, right? So where we have two vectors x and y are solved through this. Okay, so it means for an eigenvector, right, is an any non-zero multiple of this. So you say that, so this is basically eigenvector, right? Okay, now let's try to test this, whether, because we say that eigenvector is any non-zero multiple of this, right? So to test this, let's try to consider, let's take the same matrix. Okay, right? So we have matrix 6, 3, 4 and 5, right? So this was the matrix, and we obtained 1 and 4 as a vector, eigenvectors, right? So it means if you try to solve this, -6 into 1 plus 3 into 4, okay, then 4 into 1 plus 5 into 4. Okay, so that is 6 and 24. Okay, right? So if you take lambda v now, okay, so lambda v, right? So 6, 4, 6, 24, right? So you can see this, right? So whatever the eigenvector that we have obtained, right? So it is basically the same or the multiple of the eigenvector of if you take any matrix when we find an eigenvalue as well as an eigenmatrix. Now, if you see the applications of this, we have a lot of applications here, right? So we have this eigenvalues and eigenvectors can be applied for a communication system, or designing a bridge, right? Or designing a car stereo system, or in an electrical engineering as well as a mechanical engineering. Okay. Now, let me take one simple example, right? In fact, let us say that I'll take one simple application, right? Suppose I want to find out the most important application. Let's see this. Okay, I want to find a most. Let us assume that there are n number of devices, okay, and you have n number of applications, okay, n number of applications, and each application is providing some services. Okay, so it means I have n number of devices. Upon these devices, there will be n number of applications that will be executing. Okay. Now, suppose I want a specific services that has to be ranked, that has to be provided by the set of applications. Okay. In these cases, I want to make sure that, or I want to find the out of these applications, the top application which is providing the best services for a given service. Say, let's say location is a service and I have n number of applications running on my system, on my devices. Let's say this. Okay, let it be a Google API, or my search my phone, or find a friend, or there are a lot of applications that will be using this location as a service, right? Now, what we are trying here is, okay, I have a n number of applications, okay. Out of this, I am trying to find a specific service, and I want to know that which particular application is providing this services. It means the top rated or top ranked application. So now what we are trying here is, we are trying to make an arrangement in such a way that the top application will remain at the top, right? And we are trying to say that there is n number of. So let me take 6 applications. There are let's say 6 applications. Okay, 6 applications, and each 6 applications are connected in such a way that, right, each I'll represent this as a graphically. If I represent, this is application 1, application 2, and you have application 3. Okay, you have application 4, application 5, and application 6, right? Let's say that this application is executed or related to 4, even that is assuming that another application is providing the same set of services. So we are trying to represent by linking these applications, right? 1, 6, right? So 1 to 2, and let's say similarly application 2 as a service which is available in 3, and 3 as to 4, 5, Okay, and here 5 has similarly 4. Okay, 6 has interlinked with this. Okay, and 2 is interlinked with 4. Right. Similarly, 5 has another interlink. Okay. Now, what we are trying here is we are trying to look for a whatever the weightage. Here, the weightage has been given for a set of applications, right? Where the application assumes that these services are getting executed by these set of applications. Okay, so each application is relevant to another applications. Okay, so in this case we try to say that we try to generate a link vector such a way that one has a link with 4, 5, 6, right? And also 2, right? It means one has a link with 2, 4, 5, and 6. Similarly, 2 has a link with 4, right? So 4, then 3, right? Similarly, 3 has a link with 5, 4 has a link with 5, similarly 5 has a link with 4 and 1, and 6 has a link with 5. Now we try to represent this as a links, and we'll give the weightage as if there is a link, we'll give 1, otherwise 0. So this can be represented as something like this. It doesn't have the link to its own, so 0. It has a link with 1, right? 1 to 2, right? So 0, we don't have, right? So then we have 1, 1, 1, right? Similarly, for this 0, 0, 1, 1, 0, 0. Similarly, this 0, 0, 0, 0, 1, 0. Similarly, for application 4, 0, 0, 0, 1, 0. Okay. So you have 1, 0, 0, 1, 0, 0. Then here we have 0, 0, 0, 0, 1, 0. Now what we do is we try to represent these as a link matrix, right? So we try to where the rows and the columns will be representing the columnar value will be 0, 1, 0. Okay, 0, 1, 0, 1, 1, 1. So this is for A1. Let's say application 1, right? Similarly, 0, 0, 1, 1, 0, 0. Then 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0. Then we have 1, 0, 0, 1, 0, 0. Then we have 0, 0, 0, 0, 1, 0. It's a matrix, right? Okay. Now what we are trying to do here is we are trying to find the most relevant applications, right, which is providing a specific service, right? The best method is going for a probability, right? So what we do is, see, for example, application 1 as an out of six application links, right? Only 4 are possible, right? So we can write something like this as 1 by 0 by 4, 1 by 4, right? Probability 1 by 4, then 1 by 4, 1 by 4. Okay, right? This is for column 1, right? Similarly, since we have only 2 possibilities, right? So 1 by 2, 1 by 2, okay? So, and here only one possibility, so 1, 1. Here you have 2 possibilities, so 1 by 2, 1 by 2. Here you have only one possibility, right? So now, to let me rewrite this as a matrix, right? 0, 1 by 4, 0, 1 by 4, 1 by 4, 1 by 4, right? Okay. Then we have 0, 0, 1 by 2, 1 by 2, 0, 0. Okay. 0, 0, 0, 0, 1, 0. Similarly, 0, 0, 0, 0, 1, 0. Then 1 by 2, the possibilities, right? 1 by 2, 0, 0, 0, 0, 0, 0, 1, 0, right? This is our, sorry, probability matrix. Now, how do I find? See, the basic task is basically we want to find out the most important application for a specific search. The best way is we just find the eigenvalue for this. Eigenvalue. Okay. Now, for the given matrix, if you try to find an eigenmatrix, simple way, let's say this is a matrix A. So this is A minus lambda I, determinant of this, right? If you try to find this, okay. So just replace this by lambda, because we are using identity, the diagonal elements will be lambda. Okay. Now applying this, if you try to find an eigenvalue, finding the determinant of this, we'll end up with an expression 5 lambda to the power of 4 by 8 minus lambda square by 4 minus lambda square by 8. Okay, so we'll get this expression. Now, upon solving this, we'll get a result as, okay. So the lambda value will be minus 0.72031, comma, minus 0.13985 plus or minus 0.39401 and one more 0, comma 1. So when we start ranking, so basically what we are doing, we want to top a specific application which is providing a best service, right? So when performing a ranking, we'll consider the non-negative real numbers. So hence 1 will become a eigen value. See, these are all the eigenvalues, but when we are considering trying to top the rank, we will consider the non-negative values, right? So for this we'll calculate the eigen vector. So once we perform this operation, we'll get something like this, a vector 1. See, of course, we'll be giving v1, v2, v3, v4, v5, v6, right? And we'll try to solve this. Upon solving this, we'll get a vector as 1, 4, 1, 0.5, 5.5, 8, and 1, which is a transpose of this, right? Now, since 8 is the highest value that we have got, right? Sorry, 8 is the highest value, and these are A1, A2, A3, A4, A5, and A6, right? Since A5 has an highest value, it means the highest rank, right? So that's the reason it appears at the top of an application. It means if you have noticed, there will be an n number of applications running on our devices, right? This is an example where in a stock or anywhere, if you consider a device applications itself, if I want to rank the top rated applications, we can straight away use an eigenvalue and an eigenvector here. Okay, so this particular example demonstrates that by using an eigenvalue and an eigenvector, we can rank these applications and we can rate the top rated applications also, right? So this is with respect to okay, right? Now there are certain advantages as well as disadvantages if you're using eigenvalues, right? Basically, this will allow us to solve any n-dimensional problem in a linear time, which is a computational optional. And eigenvalues are basically the magnitudes of the eigenvectors. So the disadvantage is like we have to calculate them for each problem until unless you have a degenerate special cases, right? Now, second thing is we should try to understand what is LU decomposition. So when we say that we are trying to decompose a matrix, this is one of the method to decompose, to reduce the set of matrices, right? So basically this is one more method that is used to solve a simultaneous linear equations, right? So the conditions are like factorization methods are is all principal minors of the matrix, which should be a non-singular. Okay. Otherwise, there will be no formation of lower and upper triangular matrix. Right. A square matrix that does not have a matrix inverse. A matrix is a singular if only if its determinant is 0. Right. So if you consider a non-singular matrix A, that one could conduct a Navier-Stokes elimination, forward elimination steps. So we can write that as an A is equal to LU, where L is a lower triangular matrix, U is an upper triangle matrix, right? So here A can be decomposed into two parts, L and U. If you observe here, right, the diagonal elements will be 1, right, and you have a U is same as the coefficient matrix at the end of the forward elimination step. Similarly, L is obtained by using the multipliers that were used in the forward elimination. Okay, so now basically to solve linear equations, right, we'll be using LU decomposition method, right? So suppose now let's try to solve this, right, in a linear decomposition methods. So given a matrix AX is equal to B or C, right? So we try to decompose that A into LU, and then what we do is LZ is equal to C, and to obtain a Z. Similarly, UX is equal to Z for obtaining a value of X. Right? So we try to solve AX is equal to B problem. Right? So if we take an example here, right? So let me take one a simple example, right? So let's consider, right? So you have x1 plus x2 minus x3 equal to 4. Okay. So then you have x1 minus 2x2 plus 3 into 3 is equal to some minus 6. Okay. Then you have 2x1 plus 3 into 2 plus x3 is equal to 7. Right? Now, what we do is we'll try to represent this in the form, right? Ax is equal to b. So it means, right? 1, 1, 1, minus 1. Okay? 1, minus 2, 3, 2, 3, 1 is a matrix A, and you have x1, x2, x3 is equal to 4 minus 6, 7. Okay, so this is in the form of A x equal to B, right? So it means that is
-1 होगा first row 1 -1 -1. Sorry sir,
sorry.
in the first row 1 -1 -1.
Sorry, this is plus plus.
Okay sir. Sorry sir.
Fine. Sorry. Yeah. So what we do is we can solve this system using LU decomposition. So to do this, what we do first thing is, so we try to find a determinant of A is equal to LU, right? So we try to determine A is equal to LU, and we try to substitute that to AX is equal to B, right? So now what we do is we'll try to solve LUX is equal to B, right? So we are trying to replace A is equal to LU means AX is equal to B, AX is equal to B. So that becomes LUX is equal to B for X to solve this system, right? So I'll just write for X to solve the system. Okay. Let us say that UX is equal to Y. Okay. So then of course it becomes LY is equal to B and UX is equal to Y. Right? So this is LY is equal to B and UX is equal to Y. Right? So now what we do is we'll try to solve this, right? So the thing here is we want to find A is equal to LU, right? Okay. Now how do I find this? How to determine these things? Okay. So let's go with this, right? Now let me write down L is equal to I'll just write it down as like this. You have upper 0, okay, and you have a diagonal, right? Elements 0, right? Just write it down like this, right? And you have a matrix A is equal to 1, 1, minus 1, 0, minus 3, 4, 3, 1, right? Okay. Now let's take do a row operations here. Okay. So what we do is to make it this as a 0, right? So what we have done is minus 1 R1 plus R2, right? So to get this, see our initial matrix was this. Matrix A is 1, 1, minus 1, 1, minus 2, 3, 2, 3, 1. Right? This was the initial matrix. For this, okay, if you apply this, after applying this, right, so we'll get this 0. Now what we do is, the negative of this, take the negative of this and place it in the matrix. Negative of minus 1 is 1. Okay, so I'll just represent this as a new value. Okay, now, so now applying this matrix, now let us say this, if I minus 2 R1 plus R3, okay, I can make this as 0, right? There is a delay. Okay. So what I'll do is I'll get one more value as L is equal to 2 minus 2 positive value is this is 2. Okay, there is a delay. Okay. Similarly, so now by applying 2/3 of R2 plus R3, okay, right? So we will obtain 1, 1, minus 1, 0, minus 3, 4, and 0, 0, 13 by 3. Okay, right? So this is what we'll get. Now negative of 1/3 is, right? So okay,
ಇಲ್ಲ
minus 1/3, right?
ಇಂಟರ್ನೆಟ್ ಏನಾದ್ರು ಡೌನ್ ಇತ್ತಾ?
1/3, right? So it means whatever the final result that we got here, if you observe here, this is basically U, and we have got L also parallelly. So what you just do is a very
ಇಲ್ಲ ಅಲ್ಲಿಂದ
simple,
ಜಾಸ್ತಿ
okay, just make the diagonal elements as 1 and make it as zeros, the upper
ಇಲ್ಲ
matrix
ಅದು
triangle.
ನೆಟ್ವರ್ಕ್ ಪಾಸ್ವರ್ಡ್ ಆಮೇಲೆ ಕನೆಕ್ಟ್.
Hello. Yeah. Okay. So please observe here. Applying row operations here.
Can you repeat it? Can you repeat it?
As zeros. Okay. So to do that, whatever the value that we are trying to multiply, okay. So that you just replace the negative of that to L. That gives you a new and U. Okay, so you have a new matrix U as well as L, right? Now the very first thing is, now we have
Sir,
to
can you repeat this step? Please repeat, sir.
Yeah, definitely. See here. See, just to find L and U, see, I have a matrix A. I want to find out L and U, right? So while decomposing this, right, as you notice, you can please just notice here. So the diagonal for an L matrix, right, the diagonal elements will be 1, right? So you have all zeros at the top, right? All right. So and similarly for U, the lower triangular values will be zeros. Okay, right? So to obtain like this, what we do is, see, I have an A, right? So what I do is I'll try to make the values that are here to zeros, right? So the intention is I want to make this as 0. So what do? So to make that as 0, right? So initially, what do I do? So I try to solve this, right? How do I make the second row first element as 0, right? To make this, right, we have to minus R1 plus R2. The row operation will give you this minus R1 plus R2, right? See, that's you just refer this matrix. You have, this is the A matrix. I want to make this element 0. What do? Minus R1, right? So minus R1
Sir,
plus
question is, if it is already 0, then what?
So you don't have to do anything, right? See,
Okay,
if you
okay.
already have a 0, then you go with the next one. Okay?
Okay. Thank you, sir.
Okay.
Now got it. I got it.
Okay. So this is clear again, right? So you have obtained a U and you have obtained a L, right? So you now you have A is equal to LU. So you have already obtained, you have decomposed A into L and U. Okay. So I'll just rewrite the same thing. Okay. So you have 1 0 0 1 1 0. Okay. So you have 2 minus 1 by 3 1. Okay. So basically what we are trying to do is we are trying to solve Ly is equal to B. Please understand this. Okay. Then we are trying to find Y1, Y2, Y3. Okay. 4 minus 6, 7. Okay. Now this will give us Y1 is equal to 4. So of course Y1 plus Y2 is equal to minus 6. That will give you Y2 is equal to minus 10, right? So substituting this for 2Y1 minus 1 by 3 Y2 plus Y3 is equal to 7, right? You will get Y3 is equal to minus 13 by 3, right? Okay. So this is, we are trying to solve Ly is equal to B. Similarly, we have to solve Ux is equal to Y. Since we have obtained Y, right? So 1 1 minus 1 0 minus 3 4 0 0 13 by 3. Okay, this is okay. You have x1, x2, x3. Okay, so that has led to 4 minus 10 minus 13 by 3. Okay, so x1 plus x2 plus minus x3 equals 4, right? So you have minus 3x2 plus 4x3 is equal to minus 10. So of course you have 13x3 is equal to minus 13 by 3. So we have x3 is equal to minus 1, right? x3 is equal to minus 1. Similarly, we will get x2 is equal to 2 and x1 is equal to 1, right? So what we have done here is the same set of linear equation problem. We have decomposed that into LU, right? So from LU, we tried to solve that. We have obtained x and y values, right? So I just repeat the steps. For a given matrix A, decompose that into L and U. Okay, then of course the L and U have the upper diagonal matrix will have a zeros for L, and lower diagonal matrix will have a zeros for our U. Okay, so by decomposing that, you can get the values, right? Now, next thing is the singular value decomposition, right? So this is another method that is used to decompose the matrices, the given matrices, right? Now, how do I do this? Okay.
Sir, I have a question.
Yes.
Okay, say eigenvalue is basically used for dimensional reductionality, right?
Yes.
Similarly, LU is also used for the dimension reductionality, or any other applications are there?
Yes. Yes. See, we can apply it for reduction method or the decompositions, right? Of an image decomposition and all.
Okay.
Right. So next is the SVD, right? So now basically SVD is a singular value decomposition, right? Now what we do is, see, let me take a simple example where I try to use an SVD here. See, basically there is an n-dimensional problem and I want to reduce that to a lower rank matrix, right? So see, if I were take an example, see, let's say I have a 4x4 matrix. Assume that you have a 4x4 matrix, and I want to enter some 16 entries to know this, what exactly, how this particular matrix is behaving. Okay. Now, if it is very simple, right? What we do is we'll try to decompose this into lower ranks. It means we try to make sure that the high dimensional matrix into rank 1 matrices. Okay, so when we do this, we try to find the approximation of this. The approximation of sum of ranks will give you the SVD here, right? So basically here when the SVD deals with decomposing a matrix into product of 3 matrices. See, the general given for a given matrix, if I want, let's say there is an image. I want to compress this image. Let's say this. Now, by this image matrix, I cannot directly do this. So what we do is we go with a reduction methodology. So the dimensionated SVD is one of that method. What we do is a single matrix has been divided into 3 components. One is U, S, V transpose. Okay. So U is an M cross M matrix, which is a left singular vector, or we can also call this as a columnar vector. Okay. So left singular or a columnar, right? Or having an orthogonal matrix, right? Whereas S is a sigma, right? Sigma represents a set of eigenvalues, right? Sigma is a diagonal non-negative entries, right? And V transpose is a singular, another right singular vector, okay? So which is a basically eigenvector itself, right? So sigma is an eigenvalue, V transpose is an eigenvector, and U is basically a columnar matrix. Okay, so what we do is a single matrix will be divided into 3 different components. So suppose if you consider a 2 cross 2 matrix, right? The column, whatever the rows that we consider, the column values, right, will be represented as U, and the sigma are the diagonal elements, right? V transpose is another right singular vectors. Okay. Now to compute this, to compute the rank of a matrix, right? Sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose. Suppose if you have a 3 dimensionals here, it keeps on extending, plus sigma 3 U3 V3 transpose plus sigma 4 U4 V4 transpose, right? So we keep on increasing these things. Okay. Now suppose if I take on basically Where do we use this? So before going to the example, right? How to decompose this? Okay. So basically, SVDs are widely used in the calculation of other matrix operations like matrix inverse or also data reduction methods in machine learning, right? And it can be used in least square linear regression or image compression or denoising the data. So it is used as a data preparation technique to create a projection of a sparse data set prior to fitting a model, right? So if you consider a data representing dimension of n-dimensional feature spaces like rows of data as a points in that space, and SVD basically is a technique from a linear algebra that can be used to reduce the dimensionality, right? So now how do we do this? What is the methodology for this? So let's suppose if I consider a 2 cross 2 matrix, you compute its transpose itself. A is a matrix, A transpose, and then compute A transpose into A. Then determine the eigenvalues of A transpose A and sort these in descending order, right? So in the observation, it means the square root of these to obtain a singular value of A. Now again you construct a diagonal matrix S by replacing these singular values in a descending order along with diagonal. So that will be computed to S inverse, right? Now use this ordered eigenvalues, whatever we have obtained from step 2, right? And compute the eigenvectors. So now this basically these eigenvectors along the columns B, we compute a transpose B2. Then we compute U is equal to A B S inverse. To complete the proof, we will use the SVD full form, right? So again, we'll compute A is equal to US V transpose, right? So let me take one simple example here. So to find SVD, let us consider some C matrix -1, 7. Okay. So we have to decompose this C to U sigma V P. So this is what we are trying to do. See, basically, sigma U and V are the columnar orthogonal matrix, right? Sigma is a diagonal element, diagonal matrix which contains a non-negative entries, right? Now the same thing, what we can do is we can represent this as, right, C transpose C, which is equal to V sigma transpose sigma V transpose, right? So let me call this as an expression 1. Now here you can say that you have an U transpose U. See, basically why in this case U transpose U from an orthogonal matrix property, U transpose U will give you the result as 1, right? U transpose U is equal to 1. Okay. So what we do is CV is equal to U sigma, right? So let me call this as an expression 2, right? Now what we are trying here is we are trying to solve equation 1 and equation 2 to find V sigma and U. Okay, right? So what is the first step? First step is to compute this, right? C transpose C, right? So let me compute that. C transpose C equals 5 minus 1, 5, 7. So the transpose of this will give you 5 minus 1, 7. So that will give you 26, 18, 18, 74. Okay. So then equation 1, right? So now the equation 1 where you have a diagonal matrix of C transpose C. Now we need to find out the eigenvalue for this. So eigenvalue is this. right? Sigma transpose sigma, right? So which will be basically lead to an eigenvector columns of V, right? So now how do we find the eigenvalues, right? So we have determinant of C transpose C minus lambda I. Okay, so that leads to 26 minus lambda 18, right? 1874 lambda. Okay, now so which is minus 100 lambda plus 1600, right? So the eigenvalue we will get is 20 and 80, right? So which is a lambda. So we have two eigenvalues here. Okay, right? So now having obtained this eigenvalue, right? Now we have to find out the eigenvector, right? So to find the eigenvector, of course, we have two values. One is 20 and another is 80, right? So what we do is, okay, so let's say C transpose C minus 20I, right? This is basically we are trying to find the eigenvectors, right? So that is 16, 6, 18, 18, 18, 54. Okay. Now this has resulted in, so minus 3 by root 10 and 1 by root 10. Okay. So similarly, so I'll just delete this. Similarly, for CT C minus 80I, okay. So minus 54, 18, 18 minus 6. Okay. So the eigenvector.
Sir, in the last step, say
Yeah.
you have converted into a column vector. Can you repeat last step?
Previous one.
Yes, yes.
So to find an eigenvalue, right? See, we are trying to compute the eigenvalues here, right?
Sir, you have converted a 6, 18, 18, 54 matrix into a, say, some other.
1854, right? The previous one, let me see, 6, 18, 18 and 54, right?
Yes.
Right? So this is for eigenvector 1. See, we have lambda, right? We got lambda as 20, 80. We got two values, right?
Yes,
Okay.
sir.
Yeah. So we are trying to substitute that for this. C transpose, instead of 80, you can replace it by 20. That will result in this value. Okay. So that will give us.
Say, then say after calculating this 6, 18, 18, 54, you have written something else.
See, that is basically we are trying to find the eigenvector, right? In the previous example, hope you remember, I discussed about this, right? How to find an eigenvectors.
Okay.
Right. So instead of, see, I am running out of time. That's the reason I just straight away wrote the values. Okay. So where we have to find out that vector once again by applying AV is equal to lambda V, if you remember, right? Where we have to solve that V value. So in this, since it is a 2 cross 2 matrix, we'll get V1 and V2 as two vectors. Clear?
Okay, sir.
Okay. So I straight away write V2 will be 1 over root 10 and 3 over root 10. Okay. Now finally, now we have vector V, right, as minus 3 by root 10, 1 over root 10, okay, and 1 over root 10, 3 over root 10, okay. So, and we have sigma is 2 root 5, 0, 0, 4 root 5, okay. So, because from 20 and also 80, okay, we have obtained this, right? Now, since finally we have V here, we have sigma, and now we have to find out U here, right? So CV is equal to U sigma, right? So substituting these values, right? We'll get CV is equal to, right, minus root 10, 2 root 10, root 10, and 2 root 10. Okay. So finally, sigma U is equal to U sigma, right? Sigma U is equal to U sigma, right? So finally, from this, we will get all the three matrix, okay, three matrix U, V, and sigma. So what basically you are trying to do? I have one matrix. We are trying to decompose that into three components, right? By applying a SVD method here, right? So basically, we are trying to reduce the rank of the matrix, right? So with this, right? See, these are the values that has been already computed using Python, right? So what I do is I'll just try to demonstrate the applications, right? So, right. See, these are the applications that can be performed using SVD. One is image compression, image recovery, eigenfaces, spectral clustering, as well as a background removal from a video, right? So basically, to implement this, we can use a SVD in Python or truncated SVD from scikit and randomized SVD in scikit. So where you don't have to write a complete code for this, straight away you can utilize these things. Okay, so let's see that. Okay, see, basically here what we are trying here is I'll try to load an image. Before that, yeah. So just to show you that how the eigenvalues are can be computed here, straight away we can run this and we'll get a result like this. The vectors which are scaled by the lambda values. Okay. Now for an SVD, let me take one. We have two options, in fact. Okay, one is for all square matrix and another is non-square matrix. Also we can do this, right? So before that, let me apply this for an image processing, right? I have already loaded an image here. Okay, so if you run this before this, right, you can see this. We don't have to compute too many things, just you can import the packages, right, and use these things to compute the SVDs also here. Okay, just see this. Can you see this? See, this is a image, the normal image, the original image. When we decompose this for n compression, C is equal to 3, 5, 10, 15, right, 20. So when you start this, it means basically this is the approximation of the ranks, So sum of approximation of rank starts from rank 1. Then it means if you observe here in this particular slide, right, sigma 1, U1, V1, that's for one image. If you want to reduce that, again plus sigma 2, plus sigma 3, plus sigma 4. You can increase these values to obtain these set of values. Okay, and Another application for this is the dimensionality reduction. So just a minute. For a square matrix, if you consider a square matrix, okay. So I have considered the same example, whatever I have taken, right? So I explained you about recommending or finding a top application. I have used the same matrix here, right? But I have applied a reduction method here. So basically what we are trying to do is we are trying to reduce the values from a higher dimension into a lower dimensional, which makes us to trace these values, right? So this is the resultant matrix, which we had a 6x6 matrix has been reduced into a 6x2, right? So where the multiple features can be combined to a single feature. Similarly, for an non-singular also, we can perform the same thing, same operations. So this is a non-square matrix. In the previous example, the input was square matrix. Here we have a non-square matrix. Okay, right? You can see this. You have 3x10 matrix, which has been reduced to 2x2, right? Okay, so we can represent for n number of matrices. So whatever the example that I showed for an SVD as well as this, right? So we try to find the best device, right, to provide the location services, right? And also we can recommend a set of applications also, right? So I can conclude that the matrix decomposition, especially, it is very helpful in machine learning, where we train the system so that for a given matrix, if I decompose that into multiple components, each component will allow us to analyze the type of data, how these one row or a column are related to other values, right? So this is a very important concept. Hope it was useful. Thank you.
Sir, one question, sir.
Yes, sir.
Sir, using a Python software, okay, but if it's possible to find using MATLAB or not?
Yes, sir. It is possible. Yes,
Possible.
you can do that. Yeah.
Okay. Thank you, sir.
Sir, can you share this collab note?
Sorry, collab.
Can you share the collab note?
Yeah. Definitely, I can. I will share it with professor. Right.
Okay.
Yeah. Thank you.
Nice session, sir. Thank you.
Thank you.
Thank you, Dr. ShivaPrakash. It was indeed a very excellent talk on matrix decomposition, because that's the important part or the preamble for the next session, which will be handled by Dr. D.S. Guru. So I would thank Dr. ShivaPrakash for rendering this talk, and it's just a suggestion for the participant: please mute yourself. There was some disturbance in between, I just saw. So rest is okay. So don't worry about the presentation materials and all. We are collecting everything and we'll mail you. So don't worry about the test and things like that. So please be just concentrate on what the speakers are speaking, and I think it should be helpful for you. So see, at the end of the day, test is just a simple matter, but we want you to learn the internal components which Dr. Professor T.N. Nagbhushan showed you on the first day, that we should not treat a neural network or a machine learning as a black box. So don't worry, we will be there. All these videos, presentations, the codes which are there will be shared to all of you. So thank you very much for your patient listening. So we'll all break for half an hour from now. Quickly, we'll come back at 11:30 for the next session on dimensionality reduction. Thank you.